lecture 9. Again, I've given out this take-home test. I've been told that it is a hard take-home test, which is what I'm usually told, and that may very well be true. We'll grade it. We'll see what we can do on it. Do the best you can on it is my main suggestion. Okay, and again, I was hoping it would take about 3 hours. I may have been wrong about that, but let's see what we can do. Do the best you can on it. Are there any questions about specific problems, okay, or clarifications or anything else that people would like on any particular problem? Okay. A question like question.
Is the recurrence about n of k?
Okay, so question is a lot of people had questions about number 3. Problem number 3, if we remember correct, says that we want a recurrence relation to count how many strings of length n there are on an alphabet of the numbers 1 through k, such that they contain an even number of ones. Okay? And just to sort of prove that I knew what I was talking about, n, does everybody see why that there are 10 strings of length 2 on an alphabet of size 4 with an even number of ones? How many are there with strings of length 2 are there with 2 ones? Okay, there should be 1, 1, 1. Otherwise, an even number between less than 2 is 0. How many strings are there of length 0, of length 2 with no ones in it, where the alphabets, the other numbers are 2, 3, or 4? Well, there's 3 choices for the first spot and 3 choices for the second spot. So that's where 10 comes from. 10 is 1 plus 9, okay, is the first observation. The question was, give a recurrence to compute. Okay, for n, to refute n, m sub n k, the number of strings of length n on an alphabet of size k, I want you to have your recurrence work on both of these parameters. So it should be a recurrence that works for arbitrary n and k. Okay? If you can't figure out how to do that, my recommendation is, why don't you try starting out with k equals 2. K equals 1 should be pretty easy. Okay? K equals 2. And maybe try to get some kind of a pattern, some kind of an idea as to what's going on. But I'd like to ideally come up with an expression where it's dependent upon both n and k. Any questions? Okay? And that in general is a good way to do things. Okay? Is that if you get stuck on something, don't be afraid, play around with it, try to get some kind of into it. That's sort of the key to working on these kind of problems. Again, one of the problems people have expressed, not dissatisfaction, but find the last summation kind of gruesome looking. Okay? Well, the hint for that problem is actually on the start of the next page. It says it might pay to think about what the sum is doing rather than just trying to solve it mechanically. So I urge you to take a look at this sum and think a little bit about try to think what's going on. See what happens if for a particular value of k. What happens when k is n? What happens when k is 1? Okay? What happens when j is 1? What happens when j is n factorial? Okay? Play around with this a little bit. Okay? And see if you can maybe figure something out. Okay? Get some kind of an idea of what the answer is. Okay? And that might help you find it. Okay? Any questions about that? Okay? So think a little bit about what's actually going on. Play with it, okay? It's, and then maybe from there you can sort of, once you know what the answer is, it's probably easier to prove it, okay? And what I'm saying is, think about special cases here and see if you can do something with that, if that'll give you some insight into what's going on, okay? Any questions? That's a good general strategy in problem solving, okay? Any questions? The other one that I've received a certain number of questions about, okay, is problem number 6. But again, I just want to make sure people understand the definition now. What I'm really asking for here is the following. I use a word that I didn't really define so far, but it should be pretty obvious. We talked about BD sequences. BD sequences were sequences of the form for some number alpha. It was a sequence of numbers generated by the floor of alpha times I, as I went from 1 to something. I'm now interested in the first n terms of a BD sequence. Okay? For a specific type of alpha, alpha is bounded between 0 and 1, and I is never going to get larger than n. Okay? So here we're talking about a finite sequence. When I talk about a Ferri fraction, what I mean is a fraction, a simple reduced fraction whose denominator is at most n. So if n is 5, 3/5 is a Ferri fraction. Okay? 2/4 is not a Ferri fraction because it's not reduced, but 1/2 is. Okay? So every simple fraction whose denominator is at most n, okay, is what we mean by a Ferri fraction. Okay? And what I'm asking you to say here is, if you have two distinct fractions whose denominator is at most n, okay, show that at some point their BD sequences will differ. Okay? That's really what that's saying. And for here, okay, if you have any alpha, okay, be it rational, irrational, or whatnot, okay, the first n terms of its BD sequence will be identical to the BD sequence of some fraction, some Ferri fraction, meaning a fraction whose denominator is at most n, okay, and which is reduced. Okay. Any questions about that? Okay. What's it sort of aiming for? Okay. Any questions? Okay, I'd like to just quickly go over a couple of slides which I didn't go over, which might help you with this. It's something that really isn't that complicated, but just to sort of make sure that I didn't really talk too much about Ferri fractions, and it's sort of an interesting, there's some interesting things. Let me just quickly go over this thing. Basically, what we defined was that we said that when m and n, the greatest common divisor was 1, that was the same thing as saying that they were the two numbers were relatively prime. Okay? If you have a fraction m over n, we say that it's reduced if m and n are relatively prime. If m and n are not relatively prime, that means that this is a multiple of something, this is a multiple of the same thing. We can cancel it to make the fraction simpler. Now, what I'm interested in here, one thing that might be interesting, okay, is a systematic procedure to construct all proper reduced fractions. Okay? And it's sort of an amusing idea what's going on. Okay? We're going to construct all fractions that are whose denominator is not that big, which are simple and reduced, using an operation called a mediant, okay, between two fractions. Suppose, let's say, I have a fraction mn and a fraction m prime n prime. I'm now going to construct the fraction m prime n plus n over n prime plus n. Okay? Now, if you were a really bad student in grade school, this is how you added two fractions together. Okay? But hopefully you're not such a bad student. Okay? Okay, if you were when you really add fractions, you have to find the common denominator. Here we're just sort of merging the two somehow, adding the numerators and adding the denominators. Okay? What's interesting about this is that, in fact, the fraction that you get is always going to lie between the two fractions. Okay, that's why we call it mediant. Okay, it's in the median type of thing. Okay, normally if you want to construct a fraction that's between these two, exactly what you could do is you could add them up and divide by 2, and that's the midpoint between them. But this is something different. Okay, that's not what we're doing here. What we're doing is adding numerators and denominators. It's a seemingly meaningless operation. Okay, but what's more interesting here is that we can, in fact, this always lies between them. Why is that? Well, look at the following argument. Okay, my claim is that, again, we'll show two symmetric things. What I want to sort of say is that if mn is less than m prime n prime, the mediant is going to be greater than the lower number when we subtract the mediant minus the lower number, we get a number that's greater than 0. Okay? It's easy to sort of subtract these two. We find a common denominator. And my claim is that, that we really want to show that the top thing, the numerator, is greater than 0. Okay? If we can show that the numerator of this difference is greater than 0, then we know the median has to be greater than the original one. Okay? And, but an analogous proof can be used the other way. It's less than what we want to do. But let's take a look at this. Okay, if that's true, okay, what we really want to do is to say that the numerator has to be greater than 0. Is this numerator greater than 0? Let's take a look at it quickly. This numerator is n prime m to n times m prime plus m plus m prime minus m times n prime n prime. There's an mn in common here. Okay, so we can mn and minus mn. So we can cancel that out to leave us with the question of, leave us with just 2 terms. And what the remainder is going to be greater than or 0, greater than or equal to 0. If and only if you take a look at it, the positive term, nm prime, is greater than the negative term, which is n prime. Okay? Rearranging the terms shows that this will happen whenever m prime n prime is greater than m prime over n prime is greater than m over n. Okay? And that's exactly what our assumption was, okay, when we said that this was the lower end point. So the interesting thing is this median is always between the 2 fractions. Any questions about that? How people sort of believe that? Okay, good. Well, what's interesting about it is we can we can use this to build, okay, all reduced fractions in an iterative way. Okay? What we're going to do now is whenever we what we're going to do is take start out with the fraction 0 over 1, start out with the fraction 1 over 0, or equivalently, if you just want to have fractions between 0 and 1, we can have 0 over 1, 1 over 1. Those are all possible fractions whose denominator is at most 1, correct? Does anyone want to propose another one? Okay. What we can now do is construct medians between these fractions. Okay, what we're going to do is we're going to look between all fractions and construct the medians of neighboring fractions. Okay, so the median of 0 and 1 is 1/2. The median of 1/2 and 1, add the numerators, add the denominators, is 2/3. The median of 0 and 1/2 is going to be 1/3, right? 1 over 1 plus 2, or 1/3. The median of 1/3 and 0 over 1 is 1/4, 1/5, dot, dot, dot. Okay? What is the smallest fraction you can have with n as a denominator? Okay, simple reduced fraction. 1 over n, assuming it is with 0, and then there's 1 over n. If you notice what's happening, if we build this tree of medians, okay, as far as down until we only have all denominators of size n, the leftmost fraction is going to be 1 over n. Remember, this leftmost branch, the next one's going to be 1 over 5, 1 over 6. Okay? My claim that is interesting here is that this tree constructs all simple fractions. If you build the tree, okay, where you expand all fractions you can between neighbors, okay, you can construct all the fractions, simple fractions, in order of their denominators. Okay, it's in order of all reduced fractions in the order of their denominators. Okay, and so this gives us a way to generate sequences of fractions by taking this tree and building it. Okay, any questions about that? The interesting thing is, a couple of interesting things about this. First of all, what I claim is that the fractions that we build are going to be the construction of, if you sort of take this tree and you lay out sort of neighboring fractions, okay? So what are the fractions, what are the reduced fractions of size whose denominator is 1, let's say 1/5. Okay, the denominator is 5. It would be between 0, 1 and 1/4 or 1/5. we would have 2/5, which we have here, 3/5, 4/5, and the other one was 5/5, but that one's already been simplified. Okay? My claim is that by going through and doing this process, you can construct all fractions whose denominator is at most what we say. Any questions? Don't really want to go into too much detail about this. What's interesting about this? Okay, well, a couple of things. First of all, it gives us a way to construct all fractions. Okay, and there's a property, okay, about two adjacent fractions in here, which might prove useful to you in your homework, okay, on your exam. I mentioned this as a hint, okay, and so you may want to read about that. One other thing that's interesting about this, though, is that it does give us a way to approximate an irrational number by a rational number. Why is that? Let's think about what this tree of fractions is doing. Okay, what's the next fraction going to be on this side? Well, it's going to be 4/5. Okay, 4/5 plus 1/5. The median of that's going to be 5/6. It'll keep moving down that way. What I claim that's kind of interesting here is that this tree gives us an idea as to how we would approximate a given value, a given irrational number, by a fraction. Okay? For example, many of you know that pi, does anybody know an approximation for pi? Pi is everyone's favorite irrational number. What is an approximation for pi as a rational number? Has anyone ever? 22/7 is the one a lot of people have heard. Okay? But in fact, you can approximate it as arbitrarily close as you want by a rational number. How would we find such a rational number? Well, one idea I think you could use is basically do a binary search using this tree. Let's say you want to find we know that this median tree, I claim, will construct all fractions that are reduced. Okay? Let's say we want to find this pi is 3.1415926,535. Let's say the fractional part of it. Is the fractional part of it greater than or less than 1/2? Fractional part is less than 1/2. So we can go down here. Is the fractional part greater than or equal to 1/3? I believe that it's less than that. Okay? What I claim is that by going down this tree, and depending upon whether you branch lower, or each one of these fractions is refining closer and closer. These fractions are getting smaller and smaller. Every fraction is ordered from left to right. Okay? And so you know that if what you're looking for is less than something, it's got to lie to the left of it. If it's greater than that, it's got to lie to the right of it. Okay? My claim is this kind of a scheme can be used to find an arbitrarily close approximation for any irrational number. Okay? How many people sort of see what I mean and believe that? Okay, a lot of people. Okay? That and these other things that we talked about should give you some kind of an idea as to how maybe you can approach the sixth problem on the homework, on the exam. Let me just leave it at that. Any questions? So this is a scheme that will let you come up with an approximation. Okay? Again, I don't want to go into too much detail. But you can basically describe any real number, okay, any irrational number, by a string of left and right turns, okay, in this tree. Okay? And that will define an approximation to that. Any questions? Okay, any other questions about the exam? Anything? Okay. That said, I'd like to move on a little bit, okay, to sort of our next topic, okay, which is going to get us back towards combinatorics a little bit, okay? And combinatorics is, again, we know that sort of the mathematics of counting, okay? And there are a few basic counting problems that it's important that everybody know how to do when they see. Okay, these are sort of the trivial ones, okay? How many ways are there to pick k things out of n with replacement when order matters? Okay? So in other words, I'm going to line numbers up from, these are basically going to be how many strings are there of length n on an alphabet of size k, if you want to think of it that way. That's really what I'm asking for here. Because I'm sort of going to be drawing objects out but I can use them as many times as I want. That's what we mean by with replacement. Okay? If I want to form a committee of people, I'm picking you out without replacement. I can't put you on the committee 3 times. Okay? But for example, with the string problem and with other things, we can talk about with replacement. If order matters, then there's n choices for the first one, n choices for the second one, since we have replacement, dot, dot, dot. N times n, dot, 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 k times n to the k is the number of ways to pick n things out of k, okay, with replacement when order matters. How many people believe that? Okay, everybody should agree with that. What happens if we want to pick things, k things out of n, where order matters without replacement? Okay? That is basically, we've got now n choices for the first one. Once we put somebody down, because that's the first one, okay, we get n minus 1 choices for the second, dot, 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 n times n minus 1, k terms of that thing, meaning in some sense n factorial over n minus k factorial. Okay? I claim is the number of ways to pick k things out of n without replacement where order matters. Okay? Any questions about that? The final elementary counting problem is how many ways are there to pick k things out of n without replacement where order doesn't matter. So now here we're really talking about if you want to think of it this way, we could take all of these, if you think about what we have so far here we have this tells us how many ways we are to pick k things out of n, okay? We've counted every subset of things, k factorial times, because the order matters. That 1, 2, 3 is different than 1, 3, 2. If you want to count how many ways there are to pick k things out of n without replacement, order doesn't matter. We count how many things there were before and divide that by the number of ways there are to order it, which is k factorial. Okay? And so I claim that the number of ways to pick k things out of n without replacement, order doesn't matter, is n factorial over k factorial over n minus k factorial. This is such an important number, we call it n choose k, okay? And we call those the binomial coefficient. Any questions about that? Okay? Which counting problem did we leave out? Let's take a look at this thing. I have a little hierarchy of counting problems here. Okay? If I left one out, which one did I leave out? Okay? Let's stop and think about it. Okay? According to what I have, we have with replacement, without replacement. Order matters, order doesn't matter. There should be 4 different counting problems here. One of them I left out. Which was it? Okay? It's the case of counting with replacement where order doesn't matter. Okay? And this turns out to be a little bit of a harder one to count. Okay? Because now somehow you want to, it's now, let's think what the implications of that are. If you have a, this is not interesting. The implications of it are something like, if we have a string that looks like that, okay? Here's one where we say with likewise, if we're allowed with replacement, if order doesn't matter, that's the same as this string. There's only one, whether order. If I give you a string where there's lots of differences, each would be counted a different number of times. It's a trickier problem than these other 3. Okay, and that's why we left it off the page. Any questions? Okay, but now we're going to focus on the basic case of counting by binomial coefficients. And binomial coefficients are very neat things for lots of different reasons. Let's zoom it back in. Okay? The major reason why they're good things is because a lot of different counting problems end up naturally involving binomial coefficients, even if it's not completely obvious where they come from. Okay, lurking underneath them is a binomial coefficient. Okay, So somehow when you think of what a binomial coefficient it means n choose k, which is how I pronounce it. That means picking k things out of n. Okay, and the fact that we know how to do that, okay, gives us sort of a subroutine we can use for other combinatorial problems. So let's look at a more interesting a different combinatorial problem. Okay, how many heaps, complete binary heaps, can we form? Okay, out of 2 to the L minus 1 elements. Well, what is a heap? A heap is a data structure heap. Okay, it's a binary tree where each node is greater than all of its children. Okay, so 15 is the largest thing here. 14 is the largest element of its subchild. 10 is the largest element in its subtree. Okay? You may say, well, wait, why isn't 12 here? Well, the reason is because 12 is here. To be a heap, all that's necessary is that every element has to be greater than all of its descendants. Okay? It doesn't mean that the thing has to be in completely sorted order. Heap order simply means that you have a complete binary tree on a certain number of levels. Okay? And every element is larger than all of its descendants. Any questions by what a heap is? Well, how many heaps are there at L levels? Okay? Let's think about this thing. First of all, let's think, how many elements are there? If I have a heap of L levels, how many elements are there going to be? Okay? Well, I claim that if you look at the number of elements, you have 1 element on this heap. If we draw it, 1 element, 3 elements, 7 elements, 15 elements, 2 to the L minus 1 elements in a binary heap. Correct? Any questions about that? Well, when I count something complicated like this, one of the things, the best way to count things is often to build a recurrence relation. Okay? How do you build a recurrence relation? You try to think what smaller problem would help you if you knew how to count it. For a basis case, a recurrence relation, how many heaps are there on one element of level 1? Well, the heap of level 1, there's only one possible place you can put the only element you have. So it should be clear there's only one possible place to put the first element, to put one element. So I think it's clear that there's only one heap on the of height 1. In general, if I want to think of how many heaps there are of L levels, what do I need to do? Okay? Where is the largest element in the heap going to be in its heap of L levels? Where is it going to be? At the root. Do I have any choice in that matter? No. So I can put this thing here. Once I put the root down, I claim that I've got 2 smaller heaps, each of which is of level height L minus 1, right? Now, how many ways are there to break down the elements of the remaining elements from my set into 2 heaps? My claim is I've got to count how many elements there are, which elements, the total number of ways to do this, okay, is the total number of ways to figure out which elements will be in the left heap. Which elements will be in the left heap? Well, I claim I can choose the elements to be in the left heap. Any subset of elements I put in the left heap, the remaining elements will be in the right subheap, correct? Are there any partitions of the elements which would be forbidden? That if I put certain elements in this subheap, I couldn't complete the 2 to be heaps? And the answer is of course not. Okay? Any set of n elements, okay, or of 2 to the L minus 1 elements, okay, can be made into a heap, since the order is a relative order. So my claim is what we want to do is to find out how many ways can we select a subset of half the elements minus the root to be on the left side. Okay? And so what do I claim? The number of heaps of height L are, for every possible way you select elements to be on the left heap, select them out. How many ways are there to select out those elements? Well, originally there were 2 to the L minus 1 elements. 1 was the root, 2 to the L minus 2 elements. You want to pick half of them, okay, which is 2 to the L minus 1 minus 1. Okay, those are the guys that will be on the left. Once you've identified which elements will be in which set, then I claim the number of ways, what you want to do is to now try all possible ways to take the left elements and turn them into heaps. All possible ways to take the right elements, turn them into heaps. Okay? Any choice from the left, arrangement for the left, mixed with a different arrangement from the right, gives us a different heap. So I claim the number of possible ways to arrange the left times the number of possible ways of the right times the number of possible selections gives us the count. How many people sort of see this recurrence? Raise your hand if you see it. How many people are confused by the recurrence? Okay, a couple of people. Good. Okay. What am I counting? If I want to, the question is, what am I trying to do? I'm trying to count how many heaps can be built of a particular level on the numbers of L levels on the numbers 1 to 2 to the L minus 1. The root is fixed, so there's no uncertainty about the root. In general, what will any heap look like? Well, there's this recursive property that says that the left child of the root forms a heap, the right child of the root forms a heap. Okay? Once we have identified which elements are on the left, in the left subheap, that tells us by default that the other elements are all in the right subheap, correct? So let's choose all possible ways to put who's in the left subheap. This is how many ways there are to choose the members of the left subheap. Once we know the members of the left subheap, we know the members of the right subheap. So these are the number of different ways to populate things. For each way to populate something, we can now consider all possible orderings, okay, of the left side to make it a heap, and all possible orderings of the right side to make it a heap. Suppose, for example, I were to take this 11 and this 12 and this 13 and switch their spots. It would still be a heap, right? And same thing here if I swap the 8 and the 9, or if I swap the 1 and the 4. S sub L minus 1 counts the number of ways to make a heap out of these elements. Okay, once I've selected those elements, okay, this tells me how many ways there are to the left times the right times the number of possibilities. Okay, and this recurrence, I claim, counts that. Any questions? Okay, it's not necessarily an easy recurrence to solve, but what's interesting is that thinking about it from the level of choosing things, okay, it becomes easier to talk about formulating such things. So what's interesting about binomial coefficients? Well, first of all, binomial coefficients are fun, I think, because there's a tremendous number of identities that you can find on binomial coefficients. I have here a book of mine, which a book I own, I'm proud to say, called Combinatorial Identities, which is this mathematician made up a list of identities on binomial coefficients. Okay? This is pages and pages, pages of relationships about binomial coefficients. Okay? Because binomial coefficients obey certain nice properties. They're just very, very nice things to work with. And you can find some amazing properties of binomial coefficients. Again, there's more than 500 identities you can prove on binomial coefficients. In fact, using generating functions, there are techniques to automatically prove identities on binomial coefficients. So in fact, Professor Herbert Wilf, okay, has a program which automatically proves that the binomial coefficient identities. Okay, so you know it doesn't almost, it's so easy to do, almost it can almost be done mechanically. Okay? It can be done mechanically in a lot of cases. And the interesting thing about binomial coefficients is if you're brave enough to work with them, you can sort of simplify some fairly ugly looking expressions. Okay, because you have all these identities to work with. Okay, any questions? Now, many of you, I'm sure, have already seen binomial coefficients. Okay, certainly, is there anybody here who has never seen a binomial coefficient before? Okay, nobody will fess up to it. Okay, one place where you probably saw them okay, first, was when you saw Pascal's triangle. How many people here have seen Pascal's triangle before? A lot of people, okay? This is something you played with when you were in grade school. What was Pascal's triangle? Okay, Pascal's triangle said you start out with 1, you build the 1's going down here. You fill in each element as being the sum of the 2 elements on the previous row. Remember that? Okay, so this was 2. This was 1 was always on the boundary. So you always got a 1. This was going to be 1 plus 2 was 3. 2 plus 1, it's 3. For this row, we get 21 is 6 plus 15. This was Pascal's triangle, okay? And that you basically built it by taking to compute an element here, you took the element diagonally to the left of it and above to the right of it, and added them together. Now, what was interesting about this? Well, really what Pascal's triangle is a way to compute binomial coefficients. That's really what it's doing, okay? And the way to read Pascal's triangle, which frankly I always have a hard time doing it, is that as you go down the left column, what you're really getting is this is the n choose 0 diagonal. How many ways are there to choose 0 things out of n? Well, there's 1. It's sort of just 0. So this is always going to be equal to 1, 1, 1, 1, 1. This diagonal corresponded to how many ways are there to choose n things out of n? Again, there's 1. You know, you have all the things. How many ways are there to choose n, 1 thing out of n? Well, for n equals 1, there's 1. For n equals 2, there's 2 ways to choose 1 thing out of 2, right? So the diagonals here correspond to n choose k. Here they correspond, if you want to think of it, as to n choose n minus k, is the sort of diagonals going the other way. Any questions? Okay? So what's interesting? For a particular n, each row corresponds to the binomial coefficients associated with a particular n. Okay? So, for example, for n, choose 4. 4 choose 0 is 4, right? 4 choose 1. How many ways did it pick 1 thing out of 4? 4. 4 choose 2. How many ways did it pick 2 things out of 4? Okay, it turns out there's 6. If you sit down and think about it. How many did it pick 3 things out of 4? Another way to think about it is it's the same number as the number of ways to pick 1 thing out of it, because you pick the thing that you're not going to pick. There's 4 of those. How many ways did it pick 4 things out of 4? Well, there's 1. Okay? So each row of Pascal's triangle corresponds to the binomial coefficients for a particular one. Any questions? So what's interesting about binomial coefficients, about Pascal's triangle? Well, first of all, okay, it gives us a way to compute binomial coefficients, okay? And the other thing is that it gives us a way to find a lot of identities about binomial coefficients, okay, which we'll look at in a second. Any question? One thing that's sort of interesting is a quick thing. If you want to pick, let's say that I'm going to make you a bet. We're going to flip 4 coins, okay? I want to bet you, will they come up 2 heads, 2 tails, or won't they? Okay, which is a better bet to take? Okay, I flip 4 coins. Are they going to come up 2 and 2, or are they going to come up something else? How many people would rather take that comes up 2 and 2? How many people would rather take comes up heads or comes up other than 2 and 2? Okay, the majority of people are here. These are the people I won't bet with, because again, we can look at what this means. The central role here says that 4 choose 2 is 6. Okay, that means that there's 6 possible ways to pick 4 coins, such that if you think about it, let's say we want the 2 heads, okay, to be what do you call it? The 2 heads to be the things that we choose. If we choose what positions, well, one way to get the analogy of exactly 2 heads is to count how many ways are there to pick the positions of the coins that are 2 heads. Okay, so I roll the first coin, roll the second coin, roll the third coin, roll the fourth coin. I can count how many pairs of numbers from 1 to 4 are there. Okay, because what I really want to know is I want to figure out how many ways to choose 2 things out of 4. Those would be the identity of the coins which came up heads. So 4 choose 2 is 6. If you add that up, there's 16 possible ways to have 4 coins roll. Okay, so 6 over 16 is less than a half. That's not where you want to bet your money. Any questions? Any questions? How many people don't see why I get 4 choose 2 when I'm talking about coin rolls? This I may have been fuzzy about, so I'm willing to entertain any questions. Does everybody see why 4 choose 2 is the number of 4 choose 2 over 2 to the 4th is the probability for this? How many people don't see that? Okay, no one will admit to it. Okay, good. Okay, for Pascal's triangle to work, what's actually needed? Well, essentially what Pascal's triangle is doing, okay, is giving a recursive construction to construct binomial coefficients. My claim is what Pascal's triangle is saying is that R choose K is equal to R minus 1 choose K plus R minus 1 choose K minus 1. Why is it saying this? Well, you got to go back to what a binomial, the definition of Pascal's triangle is. If this is R choose K, both of them are going to the previous row, so n is down to n minus 1, and in one case we're looking to the number, in one case we're looking to the number 1 less than it. Okay? So this, I claim, is what Pascal's triangle is saying. Okay? Is the rule that's being used to construct Pascal's triangle. Okay? Why is this true? Okay? Any questions? Okay? Let's now prove this identity. This is the fundamental identity about binomial coefficients. Again, we saw it coming up in Pascal's triangle. When you work with binomial coefficients, there's 3 ways you can prove things. Okay? And I'd like to prove this particular formula 3 times to illustrate that. Okay? The first most elementary way to prove a binomial coefficient identity, such as this is equal to that plus that, would be to say, well, look, we can write everything in terms of factorials, right? What is R minus 1 choose K? It's R minus 1 factorial over K factorial, R minus 1 minus K factorial. This thing is the same, except instead of getting K factorial, okay, now this is going to be, instead of being K and R minus K minus 1, this is K minus 1, R minus K. We could add these factorials. How do we do that? Well, we notice that by canceling it, what we really get here are the terms R minus 1 dot 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 R minus K over K factorial plus R minus 1 dot dot dot, one less term than the previous level. Over here we have 1K smaller. You know, we don't get the K on. The difference between this and this is there's one more term here and one more term there. So what could we do? We could factor out the terms that we don't have, okay? And this would get left as being the R minus K term over the K term. This is going to be 1 left if we factor all those terms out. This plus 1. Well, what do we know? Well, R minus K plus K over K, okay, is R. That means that we can multiply this out. This R now can go to the front of that term, R times R minus 1 dot dot dot. We left with a K times K minus 1 factorial, we get K factorial. This, by definition, is R choose K. And lo and behold, manipulating the factorials, we've proven that this plus this equals that. Any questions about that proof? Okay? This proof has the hallmark that it is boring, okay, because it's sort of basically just working on these things, and very easy to make arithmetic mistakes on, because you have all these factorials flying around. But it is straightforward, and you could have done it in high school. Any questions? One thing that may make it a little easier to do these kind of factorial proofs, okay, is to use a slightly different notation. There's sort of falling factorial notation, where what we could say is that R falling factorial of K is the first K terms, if you want to think of it, of what you go, r falling factorial of k would be r times r minus 1 dot dot dot. The first k terms you get by repeatedly taking r, multiplying it by the previous term minus 1. So r minus 1, r minus k plus 1. That we sometimes give the notation r falling factorial of k. And it may be easier to write that than to mess with all this. Any questions? Okay. That is a boring proof. A much better proof, okay, that of the basic binomial coefficient identity is to think combinatorially. What do we know about r choose k? Okay, my claim is that it is the number of ways to pick k things out of r, correct? We could prove this identity if we could prove that the thing on the right side also counts the same thing. Okay? If this side counts Bill Gates' money, and this side counts how much money people have paid to Microsoft, and everything people paid to Microsoft went to Bill Gates, this is equal to that. Okay? That's sort of the combinatorial proof. Okay? So what can we think about? How many ways are there to pick k things out of r? Okay? Let's distinguish one of the r things. Let's say the ugliest one or the biggest one. Okay? If we consider a subset, okay, of k things out of these r things, either it contains the ugly one or it does not contain the ugly one. Okay? So I claim that all arrangements, all ways to choose k things out of r, either they have the ugly element or they don't have the ugly element. If they do have the ugly element, we know that, what do we know about it? Well, one of the k things is taken care of, okay, and the number of things, of subsets that contain the ugly element, okay, is we still have to pick k minus 1 things to fill it up out of the non-ugly elements, okay? So if it contains the ugly element, there are r minus 1 choose k minus 1 subsets of size k that do contain the ugly element. If it does not contain the ugly element, then we have to pick k things out of the non-ugly elements. There's k minus 1, r minus 1 ugly, non-ugly elements. We either pick k of them or k minus 1 of them, depending upon whether they had the ugly one. This, I claim, is proof that r choose k is equal to r minus 1 choose k minus 1 plus r minus 1 choose k. Any questions about that? How many people believe this proof? Okay. How many people don't believe this proof? Okay. The counting arguments are, in some sense, I think, the best proofs. Okay. Because they provide some kind of an insight into why this is true. Okay. Just seeing a mass of factorials around tells me nothing. Okay. But of course, they require sort of thinking about it. Okay. In a on a higher level than just manipulating algebra. Any questions? Okay. Good. The other approach, I said there were 3 possible approaches, a middle ground between a purely combinatorial proof and a purely algebraic proof manipulating factorials, is to actually use various identities that are well known about binomial coefficients. Okay? So let's now prove again that r choose k is equal to r minus 1 choose k plus r minus 1 choose k minus 1. My first claim is that r times r choose k is clearly equal to r minus k plus k times r choose k. Why is that? I add it and I take it away. It doesn't change it at all. Okay? Now suppose I have this. I can now multiply this out. Okay? I can regroup this term. This is, I claim, equal to r minus k times r choose k plus k times r choose k. Correct? It's just a question of regrouping. Now I can use a popular identity which says that n choose k is equal to n choose n minus k. Why is this true? Can anybody give me a combinatorial proof quickly as to why n choose k is equal to n choose n minus k? What is the basic combinatorial proof of this? This is the kind of thing that should be obvious. Yes, back in Ademko.
It's because in choosing k elements, you're not choosing n minus k elements.
Right. So if I want to say, for example, that you know, the number of ways of choosing k things out of n is the same as a number of ways of not choosing n minus k things out of n. Okay, and that shows that this has to be that. Okay, proof done. Okay, so that said, what do we now know? We could replace r choose k by r choose r minus k. Okay, correct? We just changing what n and r are as sort of as identical variables. Now if we've got this thing, I claim there's another identity that one can use, which is that k times r choose k is equal to r times r minus 1 k minus 1. Okay? This isn't one that I tend to remember very easily. Okay? But it's one that turned out to be very important. Okay? If so, what can we do? Well, where are we going to use it? Okay? We can take this thing. Okay? Okay, what do we have now? If we take a look at this thing, actually, where are we now going to use this thing? Okay. We are going to, I claim, oh, okay, we're going to hit, actually, let me just think about this for a second. Oh, okay, so we're going to take, I guess, this side and replace this, choose this, by, actually, wait, no, hold on. Which side are we hitting it with? Okay, I'm suddenly a little confused here. Okay, let me just think about this. Seems good a minute ago. Does anybody see where, what substitution I'm doing here? This should be pretty easy. Which one am I substituting for? Both of them. So I'm going to take this and, you're saying take this and replace it by this, and this and replace it by that. Okay. Let's say I believe that. That's a straightforward substitution. Now once we've done this thing, okay, by monkeying with the indices, I've got r minus 1 choose k, r minus 1 choose k minus 1. I've got this is equal to this times this. Dividing by r gives the original identity. Okay? Any questions about that? Okay, question? Okay, can I go over that again? Okay, what I claim is, let's take a look at this first term. Okay, k times r choose k. By definition, that is going to be, if you believe this identity, that is going to be r times r minus 1 choose k, correct? That's straightforward. Here, I've got r minus k choose this thing. Suppose I now have, if you look at this, I can apply this identity here too. Let's say that k is equal to r minus k. Okay? This times that, I can replace this by r, because that's the numerator still. R minus 1. This would be what I claimed was k minus 1. Okay? If I said substitute this k by r minus k, that's r minus k minus 1 here. So all I've done is replace this by that. That's obvious without any rewrites. This is true, just doing the substitution, k is equal to r minus k. You can see that this identity applies. Once you've got that, what do we now have? Well, choose r minus 1, choose r minus k minus 1. By reapplying this identity, okay, I can, this is sort of r, here I have, if you look at this thing, this is r minus 1, r minus 1 minus k. I can use this identity to convert that r minus 1 minus k to k. Now that I've got this, I've got r times r choose k, r times r minus 1 choose k, plus r times r minus 1 choose k minus 1. Now by just dividing by r, I get the original identity. Okay? Any questions? Okay? The truth, again, doing these kind of things, there's turned out that again, I've when you're actually doing with these things, and you're working with these kind of identities, these kind of things are usually not hard to see because you've got a lot of opportunities that we'll show in a few minutes to substitute binomial coefficients by other ones. Okay? And once you get the hang of that, this can actually usually be the easiest way to go. Any questions? Okay. What is worth knowing about what identities are there about binomial coefficients? We have seen that n choose k is equal to n choose n minus k. This is a so-called symmetry identity, and this is reflected by the fact that if you stuck a mirror down the center of Pascal's triangle, you would get a reflected thing. This other identity that we saw, which basically says that r choose k is equal to r over k times r minus 1 k minus 1, that sort of shows a relationship between an element in the Pascal's triangle and the one diagonal to the left of it. Okay. Finally, as we showed, the fact that if you sum up any row of Pascal's triangle, you get a power of 2. That shows that the sum as k goes from 0 to n of n choose k is equal to 2 to the n. Okay, and this is the binomial coefficient theorem. We'll see that again in a minute. Any questions? Okay, let's look at other identities and how you would prove them. Okay. One proof, okay, is that one identity is that whenever you have r choose m times m choose k, that there's an identity. So whenever you have the sort of the lower term here times the upper term there are the same, you can apply the following. Actually, get rid of. You can apply the following identity. That's equal to r choose k, r minus k choose m minus k. Okay, and this can be proven in a fairly straightforward way by just manipulating the factorials. I don't think I'm going to really go through that. You can do that if you wish. Okay. The other identity, which is maybe easier to see, okay, is r choose k equals r over k times r minus 1 k choose k minus 1. How can we see this one? Well, let's look at what r over k times r minus 1 choose k minus 1 is. Well, r minus 1 choose k minus 1 is basically r minus 1 factorial over k minus 1 factorial r minus k factorial. Why r minus k factorial? Well, that's what it normally is. This third term, numerator minus the denominator, the ones cancel. So that's why we've got that. If you look at this, well, this is pretty easy to see now. The r times r minus 1 factorial becomes r factorial. The k times k minus 1 factorial becomes k factorial. And now you've got r factorial over r minus k factorial, k factorial. That's exactly this. So that's about as simple a sort of factorial proof as you can get. Any questions? There are also a lot of identities associated with binomial coefficients, associated with sums of binomial coefficients. Okay? So, for example, the sum as k for all k less than n or equal to n, okay, for some n, of r plus k choose k, that means r, if k was equal to 0, that's r choose 0 plus r plus 1 choose 1. So we have incrementing both the upper and lower part of the term. Our claim is that the sum of that can be replaced by one binomial coefficient. Okay? And again, if you want to look at that one, that happens to be, again, in the table that you look at. Okay? Similarly, okay, the sum of k choose m, we're now, instead of having our count, here we have the counting variable on top and bottom of our identity. Here we have something where we have the counting variable is only on the top of the identity. So we now want to count 0, choose m, 1 plus 1, choose m, dot, 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 up to n, choose m. This thing expression can also be replaced by a binomial coefficient. Okay? Any questions? This is why working with sums of binomial coefficients can be easy. Question?
How do you define 0 to m?
Well, how many ways are there to choose 0, to choose m things out of 0 things? Okay? How many ways are there to choose 10 people out of 5 people? 0. Okay? So 0 plus 0, everything's going to turn out to be 0 till you get down to m choose m, where it's equal to 1. Okay? So it's important to agree with the convention. Okay? So we could have this sum just as easily go from m to n. Okay? But sometimes it's easier to think of it that way. Any questions? Okay? Now, let's try to prove some of these things. Again, some of these proofs are fairly easy if you think of them combinatorially. Okay? So what is a good example here? Okay? Suppose, let's say that we have, let's look at a proof here that we've got. Suppose, let's say we want to prove that, this particular sum of identities, that we want to pick m plus 1 things out of n plus 1 things. Okay? My claim is that the number of ways to pick... Okay, let's look at this. Let's look at what this sum actually is. Okay? Actually, hold on one quick second. If we want to find... Where does this summation identity come from? Let's look at the following argument. Okay? Suppose I want to pick n plus 1 things. Okay? I want to pick n plus 1 things out of n of them, out of n plus 1 things. Okay? Suppose the largest, if each one of these things is labeled from 1 to n plus 1, okay? In any subset of that many things out of that many things, there is going to be a largest element, okay? So what do we know? If the largest element that we pick, okay, is k plus 1, how many ways are there to pick n plus 1 things out of n plus 1, n plus 1 things out of n plus 1 things, where the largest element is k plus 1. Okay? Once we pick the k plus first element, now we have to finish the job by picking m elements, one less, out of the numbers from 1 to k, since this was the largest element we picked. Correct? I fumpered about this, but this should be clear. Okay? So what do I claim? The number of ways to pick n elements out of k elements, okay, can be thought of as being, okay, for any way you pick it, okay, there is going to be a largest thing. Once we pick the largest thing, there's this many ways to finish the job up. Okay? And this, I claim, proves that identity. This counts how many ways there are to pick n plus 1 things out of n plus 1 things. In every one of them, there is a largest element we picked. It might have been n plus 1. It might have been 0. Once we pick it, there's this many ways to finish the job. So this is a combinatorial proof of this identity. Okay? And once you understand that, the summation identity should make sense and should be a reasonably memorable thing. Any questions about this proof? I fear I fumpered it up a little bit. But it's actually a simple and clever proof. Any questions? Okay? Any questions? Let me go, again, here we have another identity with another, here we have another identity with a, another sort of proof where you just sort of hit it with other identities. Let me not do that, because I think we're running a little on time. But those should be pretty straightforward to reconstruct. What other things about binomial coefficients are interesting? Well, one is sort of the famous binomial theorem. Suppose we have an expression. Let's say we have the polynomial x plus y to the k. Okay, where x is a variable, y is a variable, k is a variable. K is some sort of integer. We know that x plus y squared, okay, is x times x, okay, plus y times y plus x times y plus y times x, correct? Now, because of the commutativity of multiplication, x times y is the same as y times x, correct? So if you look at what x plus y squared is, you get really, okay, 1 times x squared plus y to the 0 plus 2 times x to the 1, y to the 1 plus 1 times x to the 0, y to the 2. Okay? This is a reflection of the fact that, as you probably learned in high school, okay, x plus y to the r, x plus y to the r is the sum over all k of r choose k, x to the k, y to the k, r minus k. Why is this expression true? Can somebody give a combinatorial proof of it? Okay, let's think about what it is. It's saying, suppose we consider the x to the k, y to the r minus k term. Okay, how many instances of that are there in multiplying x plus y times x plus y dot 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 r such factors? If you think about it, each x to the k term corresponds to picking k of these r factors, where we happen to have picked the x instead of the y, if you want to think of it that way. Okay? Every possible, when you multiply x times this times that, you're constructing all possible paths, if you want to think of it. All possible choices. Each term is specified by a choice x or y, x or y, x or y. So the number of terms of the form x to the k, y to the r minus k is exactly identifying which of the k factors contain x, you pick the x for. Okay? That is sort of a combinatorial interpretation of the binomial theorem. Okay? And any questions about that? I feel I may be wandering or drifting here. So any questions? Okay? So what's interesting about this, there are a couple of interesting things about this. What is the binomial coefficient, what does the binomial theorem work out to when x and y are both 1? Okay? What is 1 plus 1? It's 2. This says that 2 to the r is equal to the sum of r choose k. What's 1 to the k? 1. What's 1 to the r minus k? 1. Really what this is, once you believe the binomial theorem, which you should believe from the combinatorial proof here, this is where we get the identity that says that summing up a row of Pascal's triangle gives us 2 to the n is equal to the sum of those binomial coefficients. It's really the special case of this. Okay? Any questions about that? Okay? That's a useful identity to know about. Any questions? There are even interesting identities, okay, about binomial coefficients corresponding to the sums of products of pairs of binomial coefficients. Okay? So look at this particular convolution. Okay? We have the sum over all k of r choose k times s choose n minus 1, n minus k. I claim that that is going to be equal to r plus s choose n. Okay? For any integer, or any time when these things are integers. Okay? Look at that expression closely. There are a couple things that are interesting about it. First thing that's interesting about it is it's the first time this semester we've seen what's called a convolution. What is a convolution? It's a sum of terms where we have one term as a function of k and the other term is a function of n minus k. Okay? So a convolution, if you want to think of it, is a sum of n terms of the form k times n minus k. Okay? Any questions about what a convolution is? Okay? It's a type of formula that comes up often enough. We'll later see some techniques for working with them. The more interesting thing is, this is another one of these identities that has a very, very simple combinatorial proof that's worth thinking about. Again, looking at trying to prove an expression like this by hitting it with identities or hitting it with factorials is wearying. Okay? But let's think what this counts. Okay? I claim that we can interpret this sum, r plus s choose n, can be thought of as how many ways are there to pick n people, okay, from r men and s women. Okay? How many ways are there to pick n people from r men and women? Well, a lot depends upon how many ways there are, how many, we can break the number of ways to pick people from men and women, break it down into classes, depending upon how many men we have in it. Okay? If we have no men in it, how many ways are there to pick, okay, n people from r men and s women where there are no women, no men? Okay? If there's no men, then we're picking no. How many ways are there to pick 0 people from r men? Well, there's one way to do it. But how many ways are there to pick? This is going to say how many ways there are to pick n people from s women. Correct? If we want to pick n people from the men and the women, if there's no men, there's s choose n ways to do it, because that's how many ways there are to pick n people from the s women. If we have one man in the pool, how many ways are there to pick n people? Okay? Well, if we know there's only going to be one man, we have to pick the man, and there's r choose 1 ways to pick the man. Once we pick the man, we now have to pick the remaining n minus 1 people from the women, right? And any combination, any way there is to pick n minus 1 women and 1 man is a way to pick n people which consist only 1 man, correct? So I claim that we multiply those two quantities, the number of ways to pick exactly k men, okay, and n minus k women, okay, is number of ways to pick n men times the number of ways to pick n minus k women. Okay? Who here understands why we're multiplying these two quantities together? Who does not understand why we're multiplying those two quantities together? Okay, no one admits to it. Okay? So what's interesting? My claim is the number of ways to pick n people is going to be the sum of this for all possible numbers of men. Correct? That is exactly what this formula is counting. Okay, now this formula should start to make sense. The number of ways to pick n people from n plus m women, and n men and r men and n s women is we sum over all k from 0 to n, okay, choosing the k out of the men and n minus k out of the women. Okay? Any questions? Okay? Once you see that, this identity should be reasonable. Now, I've shown you a lot of identities today. My belief is, strongly, that these 10 identities are really all that you need to know about binomial coefficient identities. Let's take a quick look at them now. Okay? Once you start playing with them, it's one of the things that it's not really like you have to memorize them. Certainly everything will be open book. But you have to sort of look and see what makes sense. You should know that n choose k is, again, as it is expanded in factorials. We talked about the symmetry identity today. That's a perfectly reasonable thing. That everyone should believe. The fact that n choose k is equal to r over k, choose r minus 1, k minus 1. Okay? This is something that I always find I have to look up in a book, but I know that it's there. I know that there's a way to factor out one of these terms and get a smaller termed. Okay? So that's sort of a useful thing to know. We proved the basically the formula underlying Pascal's triangle, which gives us a way to convert a binomial coefficient into two things which have smaller numerators, if you want to think of them. So that's a useful thing. Okay? What else do we have here? This gives us a way to deal with things about negative numbers. Let's not worry about them so much. Of the other ones we saw that this was the number of ways of summing up a convolution. When you have a sum of a convolution of terms, there was a way to express it. There was a sum where we were changing the top index. We could replace it. There was a sum where we were changing both the bottom and top indices. We could replace it. Okay? Notice there is no expression for one where the index is just varying on the bottom. That's sort of the only one in our repertory of identities that isn't there. Okay? And finally, we have the binomial coefficient. Okay? Any questions? Binomial theorem. Bottom line is that these relatively small number of identities let you prove a lot of things. Okay? And starting next time, we'll talk more about other identities here. Any questions? Okay. Think about it. One other thing, remember that there's pizza with the prof on Thursday. If you want to come by my office, sign up on the sheet. Okay? Thursday at noon. I'll take anybody who's signed up before 11 o'clock. See you then. Bye.